day. All right, so today what we'll do is we'll take a look at, we'll kind of differentiate between, I know you guys have heard of STP, right? Standard temperature and pressure, but then also standard states. You'll see that as well. They are slightly different from one another, so a lot of stuff that we deal with in gas laws is STP, but the stuff that we deal with here with like heat formation are always standard conditions, okay? And there's just a small difference there. We'll take a look at how you calculate heat of formation, well, heat of reaction, the standard heat of reaction from the heats of formation, okay, that we can get from a table in the back of the book because they've been determined for us. And then also we'll use Hess's law to figure out the delta H for a reaction Q, okay? So lots of different, so I guess with the bell work there, I'll go through that real quick. So the units, right? What are the units for Q? Joules. Yeah, they're always in joules. Q is almost always in joules, right? Delta H is going to be kilojoules per mole. And what are the units for C, specific heat? There we go. Joules over gram degrees C. Okay, very good. Okay, and you've got lots of different types of enthalpy, right? But even though there are different types, like there's specific types, all right? So you're looking at, oh, well, the heat of formation for this reaction, the heat of formation for dissolving something in water. It's got a special, like, little notation by it. But what doesn't change there about these? They're all delta H's, right? So all of the units for these guys are all going to be the same. They're all kilojoules per mole, all right? They're all delta H's, okay? Now, the one that you can look up in the book is this heat of formation one, okay? That's kind of the one that is slightly different than the rest in terms of its definition, all right? No worries. Just don't break the beaker, okay? Take it out of your pay. Okay, so the heat of or release, right? Because it could be positive or negative, but this is for 1 mole of a compound formed from its elements in standard state. So you look there, we have I don't know what happened there. If you look, we've got standard state down, and notice the difference between standard states, okay, and our standard temperature and pressure, right? It's 25 degrees Celsius, room temperature, at 1 atmosphere, okay, sea level, and usually you're dealing with 1 molar. So standard states are important when it comes to electrochemistry too, that we won't deal with for a little while, but it's different from dealing with gases and standard temperature and pressure. So just want to make sure that we kind of know the difference of that and that sort of thing, okay? So, and just so we're clear about like formation, right? Heat of formation, we're talking about, if we want to write the formation reaction for NO2, okay, so we're forming NO2. NO2 is the compound that's being formed, and it's being formed from its elements, okay? So from N2 and O2. So that would be a formation reaction. So the reactants are always only elements, and then you form a compound as a product, okay? So that's heat of formation stuff. And we would balance that guy like that, right? Okay. So that kind of leads you to the question like, okay, well, does, the heat of the reaction differ from the heat of formation, right? The enthalpy of formation. Well, yeah, okay, it does a little bit, right? Because in one, you're looking at a reaction, and this can happen at any state. At any state or conditions or whatever, right? In terms of, right, we're not necessarily worried so much for delta H of formation. We're looking at formation of a compound from elements. Okay, so you're looking at formation of a compound from elements, where here this is any type of reaction, right, that's going to happen. Can't read my chicken scratch, what the heck? Now, what you formation of a compound from elements. Didn't write real well. Okay, but ultimately the deal is they can potentially be the same thing, okay? This is any reaction, right? Happening in any state, any condition. Formation, we're talking about forming something from its elements, okay? So they could be, sure they could be. If we talk about a formation reaction, right? Or what's kind of more of our classic name for that reaction? When we have multiple things that come together to combine to make one thing. Call those synthesis reactions, right? So synthesis reactions, something like that. Okay. So it could be the same thing, and they better be at standard conditions, right? Yes. Oh, well, it should be delta H of F. It's a typo. Yeah. That's all. Yeah, that's all it is. It was just a typo on there. Yeah. Sorry about that. And that was what was causing the confusion. All right, good. Okay. All right. That was my writing. The heck. Be honest with me, people. Okay. All right. So let's do some delta H of reaction calculations. We call these, Miss Mars and I call this kind of the standard law, okay, for delta H. It's not really called that. Like, that's not its name. We just kind of call it that because you tend to use it a fair amount. But it's under standard conditions, so that's why we call it the standard law. We are totally making that up. If you went outside of DGN chemistry and you went up to somebody and be like, well, just use the standard law. You can calculate that. They'd be like, what are you? They wouldn't know what you're talking about. Okay, so just FYI. All right. So, but really, all it is, you guys know what the sigma sign there means? Yeah, sum, right? So it's the sum of all of the delta H of the products, right, minus the sum of the heat of formations and the reactants. So it's still, delta H is still products minus reactants, just like we've been doing, right? It's always still going to be products minus reactants. It's always going to be kilojoules per mole. Nothing's changing there. It's just another way to calculate it, okay? Let's do a few examples. Here we go. So calculate delta H of the reaction. And the nice part about, especially when you're looking at like heats of formation and stuff, you're always given the values. They give you the values every single time, okay? Because we can look them up in a table in the back of the book, right? The only time they don't is when it's like an element. And like aluminum. Notice aluminum is the only one that's not on there. You know why? Aluminum is an element. Its heat of formation is 0. Okay, the heats of formation for all elements are 0. Okay, so that's element delta H of formations equals 0 for all elements. Okay, for all elements, they're always going to be 0. Okay, so here we go. Let's do this. So delta H of the reaction is going to be equal to the sum of the delta H of the products minus the sum of the delta H of the reactants. Okay, so here we go. Delta H reaction is equal to, so the products we've got Al2O3, and that has got a negative 1676. We're going to add that to aluminum chloride, so that's another negative 704, plus 3 times 90 for nitrogen monoxide. Where'd the 3 come from? Negative the balanced equation, okay? Because we got 3 of them in there. We need to multiply the heat, the delta H of that particular compound by 3. And then for water, it's 6 times negative 42. Okay, we got that minus, all right, our products, aluminum is 0, so I'm just going to put it in there just to put it in there. Okay, in terms of our reactants, I'm sorry, aluminum is 0. And then the ammonium chlorate, or yeah, perchlorate, right, is 3 times negative 295. So here we go. We just got to break out the calculator. So 3 times negative 295. So I got minus a negative 885. So I got negative 3,562 for products. So we'll bring those together. Plus 885. Yeah, so I got negative 2,677, which would round into 3 sig figs to our answer right there below. Negative 2,680. Okay. Any questions about that? Yep. That's the reactant side. So 3 times negative 295. Oh. Salmon plus, right? So we just plug that in, that's reactants. Okay. So I did it in 2 steps, right? I just added them together just to make sure I'm doing the math right. All right, another type of problem. So you have that type of problem where they'll ask you to solve for the enthalpy of the total reaction. The other type of thing to do would be, hey, solve for the heat of formation of one of the substances in the reaction. Okay, and that's the next example here that we give you. Okay, so here we've got delta H of our reaction. It's still equal to sum of products, right, minus the sum of the reactants. All right, so I'm just going to start plugging these in here. So my products, we've got 6 times negative 393.5 for CO2 plus 6 times a negative 285.8 for water. Now I've got energy on there too. What do you guys think I do with that? Because what is this telling us? What's that telling us? Sorry.
There's energy from the reaction.
Right. The total reaction is producing that amount of energy, right? So it's what type of reaction do we have here? Exothermic. So where that goes is right over here. It's a negative 2,880. Right? That's the delta H for the reaction. So if you see energy in there, right, that's telling you what the delta H of the reaction is. Okay, you just got to make sure you got the sign right, whether it's on the reactants or the products. Okay. All right, so we've got the products right now. We got delta H there, so we subtract out our reactants. Remember, O2, it's an element, okay? So it's 0. Right, plus, for this one, this is what we're trying to find, right? Our delta H of formation for C6H12O6. Right? Okay, so let's just do some of the math here. So negative 4,075.8 plus, oops, what's that? Minus the delta H of C6H12O6 is equal to negative 2,880. I add that over. So I got 12,075.8 kilojoules per mole is equal to the heat of formation. Or I have to move that negative sign over, right? C6H12O6. Right? So I still got that negative sign in there because we're subtracting the reactants, and then I'm just going to move that over there, and we get our round that to 3 sig figs. There we go. We get our answer. Okay. Good. You okay with that? All right. So those are the two type of heat of formation problems. Either you're trying to find it for the reaction, or you're trying to find for one of the pieces. Okay. And the other one right below it is same sort of deal. You're just trying to calculate the total energy for the reaction. So it's just like the first one. It's just like the first one. So, but just in the interest of time, I'm going to pop down to Hess's law. Okay. And this is like one of my favorite things to do. It's just kind of fun problems. I like them because they're like puzzle pieces. Okay. Hess's law is pretty fun in terms of like, you're going to take a couple reactions and you got to manipulate them. You got to fit them together like puzzle pieces so they add together to give you the reaction you're looking for, that you're trying to solve for. Okay? So the deal is this. When you manipulate the equations, okay, you have to change delta H, right? So this is the important stuff to keep in mind, right? If you have to flip an equation around, whatever you do to delta, you have to do to delta H too. So whatever you do to the reaction, if we flip it over and write it the other way, we change the sign to delta H, okay? If we multiply the reaction or divide the reaction, okay, same thing impacts delta H. We're going to divide or multiply the delta H value as well, okay? So here we go. What I try to do is I look at my overall reaction first, okay? And I inspect the overall reaction, and I'm looking for things in my, they call them like elementary reactions, all right, in our little puzzle pieces here. And I want to make sure that all of the stuff lines up where it needs to go, okay, in terms of the reactants are on the reactant side and the products are on the product side, okay? So if I look at that first reaction, right, we've got NO going to N2O2. So if I look at that and I look at my overall reaction, N2 and O2 are on the wrong side of the equation. They're written in products here, but I got to have them on the reactant side, okay? So I'm going to flip that one around. I'm going to flip this one around first, okay? So I'm going to rewrite it down here as N2 plus O2 going to 2NO, all right? And remember, delta H then is now a positive 180 because I flipped it around. Okay, so you change the sign to delta H. All right. So, and this guy right here, it looks okay. All right, everything looks to be on the right in the right place and everything. So what I'm going to do is I'm just going to rewrite that and see how they add together here. Okay. So I'm just going to write that down below here. So we got 2NO plus O2 going to 2NO2. So the delta H is still equal to a negative 112. So I'm going to add these two equations together. Now, something to keep in mind is that anything that's on the reactant side and on the product side cancels each other out. Okay? So these two NOs, because I have the same number, they're gone. Okay? Two NOs are gone. And I don't have anything else to cancel out, so I'm going to add it all together now. Okay? So I'm going to add it together. I got N2 plus, how many O2s do I have here? Two. I got 2 O2 going to 2 NO2. And my delta H's we add together as well. So 180 minus 112. We get 68 kilojoules per mole, right? Now, am I almost to my overall reaction? Is that exactly my overall reaction? No, I need to do one more thing here. What should I do? Yes? Yeah, so what I'm going to do, yeah, I need half of it. So I'm going to divide the whole thing by 2. At the end, I can still manipulate it. I just got to do the same thing to delta H. Okay? So I'm going to take this whole thing here and divide it by 2. Okay? So that'll give me 1/2 N2 plus NO2 going to NO2. And then delta H is equal to 64 divided by 2 is 34 kilojoules per mole. Okay? So we're going to manipulate the puzzle pieces, add them together, and hopefully we've got all the reactants and products that we need. But if the coefficients don't quite match, you can still manipulate it at the end. Okay, you can still manipulate it at the end. You just got to do the same thing to delta H as well. Okay, and they take a little practice. These ones take some practice. All right. Okay, so that's about it. Okay. Well, we'll do the other ones here. I'll put the answers to the other ones on here as